So let's take a look at the neuron. If you look at a small portion of the axon here, the distribution of charges inside and outside the axon is such that the inside has a negative charge, the outside is positive. The inside is negative in relation to the outside. And as a result, when you place a voltmeter here, the potential that we can measure is about minus 70 millivolts. And we call this the resting membrane potential. So how does the axon maintain the resting membrane potential? How do you get that minus 70 millivolts? So to understand this, we first must remember that there is more sodium outside the cell and more potassium inside the cell. There is a protein pump powered by ATP that pushes the sodium out and pushes the potassium in. There is a leak channel, which is just for potassium, that allows the potassium to leak out of the cell from a region of high concentration to a region of low concentration. So we have a sodium-potassium pump and a potassium leak channel. The net result is that more positive charges end up leaving the cell. So the inside becomes negative. If you were to place a voltmeter on the inside, we would find out that the inside has a voltage of negative voltage, which is minus 70 millivolts. The inside and outside have opposite charges, and so we say that the membrane is polarized. So what happens when an action potential reaches the axon? The action potential is actually caused by the movement of sodium into the axon, thereby bringing positive charges into the axon. So now we went from minus 70 to 0 because the inside and outside both have positive charges. So we say that the membrane is said to be depolarized, which means there is no positive and negative sides in the axonic membrane, and the charge and the voltage is 0 millivolts. So this stage of the action potential is called depolarization phase of the action potential, and actually it passes 0 and the voltage goes even higher and reaches up to plus 20 millivolts. And we'll take a look at how that happens. We need to remember that there is more sodium outside the cell and more potassium inside the cell. So in the axon, the sodium-potassium pump is still on, and sodium is being pumped out, potassium is being pumped in. The potassium leak channel is open, and the potassium slowly leaks out from the inside to the outside. When an impulse arrives at the axon, another channel is open. We call this channel the voltage-gated sodium channel. So let's write that down. Voltage-gated sodium channel. This is a very special channel that opens only when there is an impulse that arrives at the axon. So when these channels open, sodium that has been accumulating on the outside rushes in and brings with it a whole bunch of positive charges. So when positive charges arrive inside, the voltage goes up from minus 70. It goes up first to 0 millivolts, and then finally it reaches all the way up to even 20 millivolts. We call this stage the depolarization phase of the action potential. Once the axon is depolarized, it must repolarize so that it can return to normal. So let's look at the same axon, a close-up of it. Once the depolarization, full depolarization has occurred and you have reached plus 20 millivolts, now it goes back to the original, which is the minus 70 millivolts. We call this process repolarization. which means you're going back to how we started, which means the outside will be positive and the inside will be negative. And the voltage goes back to minus 70 millivolts, which is your resting membrane potential. So what causes the repolarization of the action potential? So the repolarization phase is brought about by the movement of potassium out of the cell. Now potassium is positively charged. There is more potassium inside the axon. So when voltage-gated potassium channels open in a big way, then potassium rushes out of the axon, taking all the positive charges out of the axon and bringing the voltage back down all the way to minus 70 millivolts. This happens very rapidly because potassium gates open in a great rush. The potassium gates, they respond to the change in voltage. When the voltage gets to 0, they open and all the potassium comes out. At 0 millivolts, the sodium channels close as well. So sodium is no longer coming in, potassium goes out, and the voltage drops down to minus 70 millivolts. So let's recap what we just learned. Let's imagine that the action potential is moving from left to right. It's moving from the nerve cell body towards the synaptic terminal. So let's put a flashlight here. So as if you were moving a flashlight from the left to right. So let's imagine that the depolarization phase of the action potential is where this yellow circle is. So here, because it's the depolarization phase, the inside is going to be positive, and so the voltage is about plus 20 millivolts. We say that the membrane is depolarized. Yes? So as we move to the right, this area has not yet seen the action potential, and so it will be in resting, and so this is going to be minus on the inside and plus on the outside. And this voltage is going to be minus 70 millivolts, and we say that this part of the membrane is polarized. The part that is to the left of the action potential is the area that has just completed repolarization because the action potential has just moved away. So this is recovering. The one on the left is recovering, and so this one is also going back to negative on the inside, positive on the outside, and this area is back to minus 70 millivolts. It's on its way to minus 70 millivolts, and we say that this part of the membrane is repolarized. Even though we showed the action potential moving smoothly down the axon, in actuality, in many of our neurons, especially the ones that are involved in memory and those that are involved in movement, the motor neurons and sensory neurons, where information must move very quickly, you will have the impulse, the action potential jumping from one point to the other. So we're going to look at how that happens. This is what I'm drawing here in yellow is the myelin sheath. It is basically a covering around the axon. This is the myelin sheath. And these, in between the myelin sheath, the spaces are called nodes or nodes of Ranvier. So the impulse, the action potential actually jumps from one node to the next. And this actually increases the speed of conduction. This increases the speed of conduction, and so information can move very quickly down the neuron. This is extremely important for any kind of movement that we do. Motor neurons are those that make us move. They have to have information moving very quickly. So when you're learning something new, memory should also move very quickly. So these information through the neurons that are involved in your memory should move very quickly. So when you're learning something, in fact, this myelin actually increases, and which is why learning something over and over again is extremely important, because you need to give it time to actually grow the myelin, so you would have this advantage of information coming to you very quickly, so you can recall your memory very quickly. So this is kind of like a train going along the express track and missing all the local stops. So it's jumping from one express stop to the other, and it moves much faster. So we call this kind of conduction saltatory conduction. Saltatory. Saltatory comes from the Spanish word for jumping. Saltar, I think I'm saying it correctly, is to jump. Let's explain the whole thing with a graph. Here is time in seconds on the x-axis, voltage in millivolts on the y-axis. On the y-axis, we'll also have our voltage, minus 70, the important ones, 0, and plus 20. The resting membrane potential starts at minus 70 and then goes up as a depolarization phase of the action potential and comes down as the repolarization phase of the action potential and goes back to normal. So this is 1, resting membrane. 2 is depolarization phase of the action potential. 3 is repolarization phase of the action potential. The depolarization phase, or the rising phase, is caused by sodium going in. So we'll say inflow. The falling phase, or the repolarization phase, is caused by potassium outflow. So let's write these 3 stages down. So we have 1, which is resting membrane potential. 2 is depolarization phase of action potential. 3 is repolarization of action potential.